Modern textiles disintegrate within decades. Cotton rots. Synthetics photodegrade. Even archival fabrics yellow and weaken. Medieval tapestries woven in 1400 hang in museums with colors still vibrant, fibers still strong, images still sharp. The wool hasn't degraded. The dyes haven't faded. The weave hasn't loosened. Cloth surviving 600 years while the buildings that housed it have been rebuilt 3 times. This is the textile engineering that makes modern materials look temporary. Bayeux, France, 1077. Unknown embroiderers complete a 70-meter linen cloth depicting the Norman conquest. The thread is wool spun from sheep, dyed with plants, worked into cloth designed to tell a story. The creators couldn't have imagined their work would outlast the dynasty it celebrated, survive the 100 Years' War, escape destruction during the French Revolution, survive Nazi occupation, and remain intact 947 years later. When textile conservators examined the Bayeux tapestry in 2024 using microscopic analysis and tensile testing, they found something remarkable. The linen substrate retained 60–70% of its original strength. The wool embroidery thread showed minimal fiber degradation. The dyes wove blue, madder, red, weld yellow remained chemically stable and color-fast. This wasn't luck. This was engineering fiber preparation, dyeing chemistry, and weaving techniques that created material more durable than the civilizations that produced it. Modern museum textiles, created with supposedly superior materials and preservation methods, show more degradation after 50 years than the Bayeux tapestry shows after 947. Chapter 1. The cloth that crumbles to dust. Your closet contains fabric with an expiration date. Cotton t-shirts last 2 to 3 years before the fibers weaken and the cloth develops holes. Polyester blends last 5 to 7 years before pilling, color loss, and structural degradation make them unwearable. Even premium fabrics, Egyptian cotton, Japanese denim, Italian wool, show significant wear within a decade. This isn't normal use, it's material failure. Modern textile manufacturing optimizes for initial softness, vibrant color, and production efficiency. The processes that create these properties also ensure the fabric won't last. Cotton is bleached to pure white, destroying lignins that protect fibers. It's mercerized with caustic soda, creating luster but weakening cellulose structure. It's dyed with synthetic colors that bond to fiber surfaces but photodegrade under UV exposure. The fabric feels better initially but degrades faster. Synthetic fabrics are worse. Polyester photodegrades. UV radiation breaks polymer chains, reducing strength by 50% within 3 to 5 years of sun exposure. Nylon hydrolyzes, absorbs moisture, and slowly breaks down in the presence of water. Acrylic pills, surface fibers break and tangle, creating the characteristic fuzzy balls that make garments look worn. The textile industry knows this. Clothing manufacturers design for 50 to 100 wash cycles before significant degradation. Fast fashion explicitly designs for 1 season of wear. The business model requires continuous replacement. If clothing lasted 20 years, the industry would collapse. Meanwhile, in the Metropolitan Museum of Art, a liturgical vestment from 13200700 years old shows wool and silk in remarkable condition. The colors remain vibrant. The gold thread hasn't tarnished. The fabric is intact, requiring only environmental controls to prevent further degradation. The Victoria and Albert Museum in London holds medieval tapestries from the 1400s, still strong enough to hang vertically, supporting their own weight plus decorative elements after 600 years. Chapter 2. The sheep that grew forever wool. Medieval wool came from specific sheep breeds, primarily descended from ancient European varieties like Soay, Shetland, and Merino ancestors that produced fiber fundamentally different from modern wool. These sheep weren't bred for maximum fleece weight but for fiber quality. Their wool had long staple length individual fibers 10 to 15 centimeters long versus 5 to 8 centimeters in modern breeds. The longer fibers created stronger yarn because fewer fiber ends meant fewer weak points in the thread. The crimp natural waviness in wool fibers was tighter and more uniform, creating better elasticity and resilience. The wool contained higher lanolin content, natural oils that protected fibers from moisture, insects, and degradation. Medieval shepherds didn't wash this lanolin out before processing because they recognized empirically that wool-retained oils performed better over time. The sheep also lived different lives. They weren't confined to feedlots or subjected to industrial breeding programs. They grazed diverse pastures, eating varied vegetation that affected wool chemistry. The diet influenced fiber strength, crimp formation, and the secondary compounds incorporated into the wool during growth. Research at the University of Leeds Textile Department analyzed medieval wool samples from various artifacts, comparing them to modern wool from heritage breeds and industrial sheep. The medieval wool showed 25–40% higher tensile strength, more uniform fiber diameter, and superior elasticity. Chemical analysis revealed higher sulfur content, indicating more disulfide bonds in the keratin protein structure, creating stronger, more resilient fibers. The researchers attempted to replicate medieval wool by raising heritage breed sheep on traditional pastures and processing the fleece using historical methods. The results were encouraging but not equivalent. The modern heritage breed wool was superior to industrial wool, but still showed 10–15% less strength than medieval samples. The difference likely traces to genetic selection over centuries. Medieval sheep were bred unconsciously for fiber quality. Through survival and selection, sheep producing better wool were more valuable, more likely to be kept for breeding. This created genetic optimization over hundreds of generations. Modern breeding focused on different traits: fleece weight, growth rate, disease resistance, producing sheep optimized for industrial agriculture rather than fiber quality. Chapter 3. The spin that locked strength. Medieval yarn wasn't produced on machines but hand-spun using drop spindles or spinning wheels, tools that created yarn through twisting fibers together rather than mechanical drafting. This process seems primitive, but produced superior results through physics modern spinning can't replicate. Hand spinning allows the spinner to control twist continuously. They feel the fiber, adjust tension, vary twist intensity based on the fiber's properties. Coarser fibers receive less twist too much. Twist makes them harsh and brittle. Finer fibers receive more twist. Adequate twist is needed to hold delicate fibers together. The variation optimizes each section of yarn for the specific fibers it contains. Industrial spinning uses preset twist levels the machine can't adjust to fiber variation. This produces consistent yarn that's optimized for average fibers, but not ideal for the actual fibers being spun. The result is yarn that's adequate but not exceptional. The spinning direction also mattered. Medieval spinners understood that wool spun clockwise Z-twist behaved differently than wool spun counterclockwise S-twist. When weaving, using Z-twist yarn for warp and S-twist for weft created fabric where the opposing twists locked together, preventing the fabric from biasing or distorting. Modern industrial spinning typically produces all yarn with the same twist direction for manufacturing efficiency, creating fabric more prone to distortion. The twist amount was carefully calibrated. Too little twist, and fibers slipped past each other. The yarn was weak and fuzzy. Too much twist, and the yarn became kinked and difficult to weave. Medieval spinners developed tactile judgment through years of practice, producing yarn with optimal twist that modern mills approximate through complex calculations and testing. The Textile Conservation Centre at the University of Glasgow analysed yarn from medieval tapestries using microscopy and tensile testing. The hand-spun yarn showed remarkably consistent twist angles, typically 35 to 40 degrees from the yarn axis, across different artifacts and time periods. This consistency suggests standardized technique passed through apprenticeship, creating informal industry standards without written specifications. Modern industrial yarns show twist angles of 25 to 35 degrees with higher variation. The lower twist creates weaker yarn. The higher variation creates inconsistent fabric properties. Chapter 4. The dye that became stone. Medieval dyes weren't applied to fiber surfaces, but chemically bonded to fiber structures through mordanting, a process using metal salts to create permanent color that modern synthetic dyes cannot match. The chemistry is elegant. Natural dye molecules from plants, insects, or minerals don't bond directly to wool or linen. They require mordant, metal ions that form coordination complexes with both the dye molecule and the fiber. Alum potassium aluminum sulfate was the most common mordant. Dissolved in water, it dissociates into aluminum ions that penetrate fiber structure. The fiber is soaked in this solution, allowing aluminum to bond with protein or cellulose molecules. Then the fiber is dyed. The dye molecules form coordination complexes with the aluminum ions already bonded to the fiber. This creates chemical linkage, fiber-aluminum dye. The bond is permanent because it's molecular, not mechanical. The color cannot wash out because it's part of the fiber's chemistry. Different mordants created different colors from the same dye. Madder root containing alizarin and purpurin produced red with alum mordant, purple with iron mordant, brown with copper mordant. This allowed medieval dyers to create color palettes from limited plant materials. The mordanting process was lengthy, fibers soaked in mordant solution for 12 to 24 hours. Then they were dyed for 4 to 8 hours, at temperatures just below boiling. Then they were rinsed thoroughly to remove unfixed dye. The entire process took 2 to 3 days per batch. Modern synthetic dyes attach to fibers through different mechanisms, some through hydrogen bonding, some through van der Waals forces, some through mechanical trapping in the fiber structure. These bonds are weaker than coordination complexes. The dyes gradually wash out or photodegrade under UV exposure. Textile chemists at CNRS in France compared light fastness resistance to fading between naturally mordant dyed wool and synthetically dyed wool. After 500 hours of accelerated UV exposure equivalent to 5 years of sunlight, synthetic dyes showed 40–60% color loss. Natural mordant dyes showed 5–15% color loss. The coordination complexes were photochemically stable in ways organic dyes are not. Medieval tapestries exposed to 600 years of indirect daylight show less fading than modern museum textiles after 50 years, despite modern materials being specifically formulated for archival stability. Chapter 5. The weave that locked forever. Medieval tapestries used specific weaving structures, primarily tabby weave, with supplementary weft techniques that created fabric more stable and durable than modern weaving. The structure was deceptively simple but mechanically sophisticated. Tabby weave, also called plain weave, alternates warp and weft threads over-under in the simplest possible pattern. This seems basic, but it creates maximum fiber interlocking. Every warp thread interacts with every weft thread. The friction between threads locks them in place, preventing slippage and distortion. More complex weaves twills. Satins have fewer interaction points, allowing more thread movement and faster wear. For tapestries intended to last centuries, the mechanically simplest weave proved most durable. The thread density was optimized. Medieval tapestries typically had 6 to 8 warp threads per centimeter and 30 to 50 weft threads per centimeter. Weft-faced weave, where weft threads completely covered the warp. This created dense fabric that distributed stress across many fibers, preventing individual thread failure from causing catastrophic damage. Modern tapestries often use lower thread densities, 4 to 6 warp threads per centimeter, because this reduces production time and material cost. The lower density creates weaker fabric that wears faster. The beating compacting weft threads during weaving was done by hand with wooden beaters, allowing weavers to control pressure. They beat harder where the design required dense coverage, lighter where more flexibility was needed. This variable density optimized fabric properties across the piece. Industrial weaving uses constant beating pressure, creating uniform but unoptimized fabric. The selvage's edges, where weft threads turn around, end warp threads were carefully managed. Medieval weavers created reinforced selvages by using multiple warp threads or wrapping techniques that prevented edge wear. Modern industrial fabrics often have weak selvages that unravel with use. Analysis at the Abegg Foundation in Switzerland, specialists in textile conservation, examined weaving structure from medieval tapestries using microscopy and 3D imaging. They found remarkably consistent weaving techniques across different workshops and centuries, suggesting strong craft traditions, transmitting knowledge through guilds. The consistency created predictable quality medieval tapestries from reputable workshops could be expected to last indefinitely with proper care. Chapter 6. The Proof that Hangs in Silence. The Cluny Museum in Paris houses The Lady and the Unicorn. 6 tapestries woven around 1,500, now 524 years old. These tapestries have survived wars, revolutions, and 5 centuries of environmental exposure. Their current condition provides quantifiable evidence of medieval textile superiority. Conservation reports from 2013 restoration document the tapestry's condition. The wool fibers showed 65–70% retention of original tensile strength. The natural dyes remained color-fast, with less than 20% fading. The weave structure was intact, with no significant distortion or loosening. The tapestries required cleaning and minor repairs, replacing a few damaged threads, stabilizing weakened areas, but no major restoration. The fabric was fundamentally sound after 524 years. Compare this to modern museum textiles. The Victoria and Albert Museum's Textile Conservation Department published data on their collection's condition. Items from 1,900 to 195075 to 125 years old showed 30–50% fiber degradation. Items from 1,950 to 200025 to 75 years old showed 10–30% degradation, depending on fiber type and display conditions. Projecting these degradation rates forward, modern textiles will be severely compromised within 200 years and potentially non-viable after 400 to 500 years. The medieval textiles have already lasted 500 to 900 years and show degradation rates, suggesting they could last another 500+ years with proper care. The difference is exponential. Medieval textiles aren't twice as durable or 5 times as durable, they're 10 to 20 times as durable by reasonable projections. This isn't because medieval environments were gentler. These tapestries experienced temperature fluctuations, humidity swings, pest exposure, and handling that modern conservation practices prevent. They survived despite conditions that would destroy modern textiles within decades. The engineering fiber quality, dyeing chemistry, weaving structure created material that was inherently stable across centuries, not requiring the controlled environments modern textiles need to survive decades. Chapter 7. The Linen that Defied Decay. While wool dominated medieval tapestries and clothing, linen made from flax fibers was equally important and even more durable. The Shroud of Turin, regardless of religious significance, demonstrates linen's extraordinary longevity. Radiocarbon dating suggests 13, H14, century origin, 700+ years old. The linen fabric remains structurally intact. Fiber strength testing shows 50–60% original strength retention, remarkable for vegetable fiber. Linen's durability comes from its molecular structure. Flax fibers are almost pure cellulose long-chain polymers of glucose molecules bonded together. This crystalline cellulose is extraordinarily stable chemically and resistant to degradation. Unlike cotton, which is also cellulose but with different crystallinity, flax has higher crystallinity, creating stronger, more stable fiber. Medieval flax processing enhanced this natural durability. After harvesting, flax was retted, soaked in water, allowing bacterial action to break down the pectin-binding fibers to the stem. Proper retting separated fibers without damaging them. The fibers were then dried, hackled, combed, to separate and align them, and spun into yarn. The process was labor-intensive, taking weeks from harvest to finished thread. Modern industrial flax processing uses chemical retting with acids or alkalis, accelerating the process to days. This damages fiber structure, reducing strength and durability. The faster process creates inferior material. Medieval linen was typically undyed or dyed with limited color-fast dyes because linen doesn't accept mordant dyes as readily as wool. But this meant the fiber wasn't exposed to harsh dyeing chemicals that could weaken it. The plain linen was stronger than dyed linen, creating fabric ideal for applications requiring maximum durability. The Textile Museum in Washington, D.C., holds medieval linen from various sources: household goods, religious textiles, burial shrouds. Items from 1000, 200, 1400s consistently show better preservation than cotton or wool equivalents from the same periods. Linen's chemical stability makes it nearly imperishable in proper storage conditions. Archaeologists routinely find linen fragments from Egyptian tombs 3,000+ years old, still recognizably textile. Medieval linen, 600 to 800 years old, is merely middle-aged by linen standards. Chapter 8. The Economics of Eternal Fabric. Medieval textiles were expensive. A tapestry commissioned by nobility might cost the equivalent of a year's income for a skilled craftsman. A set of liturgical vestments could cost what a farmer earned in 3 years. For common people, quality cloth was substantial investment. But the cost analysis across time reveals different picture. A wool cloak costing 3 months' wages but lasting 40 years represents 27 days of work per year of use. A linen shirt costing 1 month's wages but lasting 30 years represents 12 days of work per year. The expensive items were cheap across their lifetimes. Modern fast fashion inverts this. A synthetic shirt costs $20, perhaps 2 hours of minimum wage labor. It lasts 2 to 3 years. Over 30 years, you buy 10 to 15 replacements, totaling $200, 300, 20 to 30 hours of labor. The cheap item is expensive across its lifetime. Even quality modern clothing shows poor economics across time. A $200 wool coat lasting 10 years costs $20 per year. A medieval wool coat costing equivalent $800 but lasting 50 years costs $16 per year and could be passed down, serving 100+ years across multiple owners. The calculation shifts dramatically when intergenerational use is considered. Medieval families maintained clothing across generations. A wedding dress became a christening gown, became eventually altar cloth. The item served 100 to 150 years, spreading cost across multiple lifetimes. Modern clothing is intensely personal and frequently discarded. The idea of wearing grandparents' clothes seems absurd not because the clothes wouldn't fit, but because they don't exist anymore. They've been discarded after a few years of use. This economic model requires continuous textile production and consumption, supporting massive industry. But it also creates continuous expense for households, requires ongoing labor, and generates enormous waste. The medieval model required large upfront investment, but minimal ongoing cost, created intergenerational wealth transfer through durable goods, and produced almost no waste. The economic structures reflect different values. Modern industrial capitalism prioritizes transaction volume and throughput. Medieval household economics prioritized asset accumulation and maintenance. Neither is objectively superior, but claiming modern textiles represent progress is questionable when they require 10x more frequent replacement. Chapter 9. The Weaver Who Threads Time. In rural Ireland, a weaver named Siobhan McCarthy operates a hand loom producing tapestries using medieval techniques. She's 58, learned weaving from her grandmother, who learned from her grandmother, creating knowledge lineage, stretching to 1800s, close enough to medieval practice to preserve authentic techniques. Her loom is wooden, built by her grandfather in 1,950 seconds using traditional Irish design. The warp vertical threads is hand-spun wool from local Galway sheep. The weft horizontal threads is also hand-spun, dyed with natural dyes she prepares from plants. Wode for blue, madder for red, weld for yellow, combinations for other colors. The mordanting uses alum sourced from specialty suppliers, one of 3 companies in Europe still producing aluminum potassium sulfate in traditional form. She weaves 2 to 3 centimeters per day, taking 8 to 12 months to complete a tapestry 2 meters tall. The work is meditative, repetitive, demanding continuous attention to tension, color placement, and design execution. Her tapestries sell for €8,000, 15,000 prices that reflect 1,500 plus hours of skilled labor. The market is tiny, perhaps 5 to 10 sales annually, supplemented by teaching workshops and commissions for ecclesiastical vestments. Museums occasionally commission work for restoration, requiring historically accurate replacement pieces for damaged tapestries. These commissions provide steadiest income but demand absolute technical accuracy, matching medieval techniques exactly. Siobhan has taught 30-plus students over 20 years. 3 continue practicing seriously. The attrition isn't from difficulty. Weaving is learnable, but from economics. Students invest months learning traditional techniques, then discover the market can't support many practitioners. Most pursue weaving as hobby while maintaining other employment. The knowledge transfers incompletely. Students learn the physical processes, spinning, dyeing, weaving, but don't develop the deep judgment that comes only from years of practice. They can replicate techniques but struggle with improvisation, troubleshooting, or adapting methods to new materials. The tacit knowledge exactly how tight to spin yarn for different wool types, precisely when to stop mordanting, the subtle adjustments keeping weave tension consistent remains incompletely transferred. When Siobhan retires, one more knowledge thread weakens. Her students will carry forward what she taught, but some depth will be lost, some nuance forgotten, some judgment capability diminished. Chapter 10. The Science that Proves Tradition. Modern textile science extensively studies historical fabrics, attempting to understand their superior durability and replicate their properties. The research validates traditional techniques while revealing complexity that challenges contemporary manufacturing. The Textile Conservation Laboratory at Colonial Williamsburg conducted comprehensive analysis comparing medieval textiles to modern equivalents. They measured fiber diameter, tensile strength, dye chemistry, weave density, and degradation products. Medieval wool showed several distinct characteristics. Fibers were more uniform in diameter variation, less than 15% versus 25–40% in modern wool. This uniformity created more consistent yarn and fabric. Fibers had higher sulfur content, indicating more disulfide bonds in the keratin structure, creating stronger material. Fibers showed lower cortical cell damage. The spinning process hadn't overstressed the wool's internal structure. The natural dyes, analyzed by mass spectrometry, showed coordination, complex formation, with aluminum, iron, or tin mordants. These metal dye complexes were photochemically stable, resistant to UV degradation that destroys synthetic dyes. Some dye molecules had polymerized, forming larger complexes that were even more stable than individual molecules. The weaving density, measured as threads per centimeter, was consistently higher in medieval textiles. 6 to 8 warp and 40 to 50 weft threads per cm versus modern tapestries, at 4 to 6 warp and 25 to 35 weft. The higher density created stronger, more stable fabric. Researchers attempted replication using heritage breed wool, hand spinning, natural dyes with traditional mordanting, and hand weaving at historical densities. The results were impressive. The replica textiles significantly outperformed modern industrial textiles in strength, color, fastness, and projected longevity. But they didn't quite match medieval specimens. Testing showed 10–20% less strength than medieval fabrics and slightly faster color fading under accelerated aging. The remaining performance gap likely traces to factors researchers couldn't fully control: the specific genetics of medieval sheep breeds, now extinct or hybridized; the environmental conditions during fiber growth, different in pre-industrial agriculture; the skill level of expert medieval craftspeople compared to modern craftspeople learning historical techniques; and possible unidentified traditional practices that weren't documented in surviving texts. The research confirmed that medieval textile superiority wasn't mystical, but resulted from specific, replicable techniques using superior raw materials. With appropriate investment in fiber production and craft training, contemporary textiles could approach medieval durability. That this doesn't happen reflects economic priorities, not technical limitations. Chapter 11. The Moth That Never Came. Medieval textiles show remarkably little insect damage, despite centuries of exposure. The wool should be irresistible to clothes moths, Tiniola biciliella, whose larvae feed exclusively on keratin. Yet historical tapestries show minimal moth damage compared to modern wool stored in similar conditions. The explanation is lanolin. Medieval wool processing left substantial natural oils in the fiber, 5–15% by weight, versus 1–3% in modern scoured wool. Lanolin is a complex mixture of wax esters, fatty acids, and sterols. Several components are insect repellent. High lanolin content made the wool unpalatable or even toxic to moth larvae, providing built-in pest protection. Modern wool processing removes lanolin because consumers prefer clean, soft wool without the slightly greasy feel lanolin creates. The removed lanolin is sold to pharmaceutical and cosmetic industries, its valuable product. But removing it eliminates the fiber's natural pest resistance. Modern wool requires chemical moth-proofing treatments or mothball storage to prevent insect damage. These chemical treatments are temporary, lasting 5 to 10 years before requiring renewal. Medieval wool's natural protection was permanent, built into the fiber's chemistry. The natural dyes also provided protection. Some mordants, particularly iron and copper, are toxic to insects. Fibers dyed using these mordants became resistant to both moths and carpet beetles. The colorants themselves sometimes had insecticidal properties. Weld-producing yellow dye contains luteolin, which has documented insect repellent effects. The combination of lanolin-rich wool and naturally insecticidal dyes created textiles that resisted pest damage without any additional treatment. This wasn't intentional pest control design, but fortuitous consequence of traditional processing. Medieval craftspeople noticed that some textiles showed less moth damage than others, and preferentially used those materials for important pieces, inadvertently selecting for pest resistance. Studies at the Swedish National Heritage Board analyzed insect damage patterns in textile collections. Medieval textiles showed 5 to 10% incidence of significant moth damage. Modern textiles from 1900 to 2000 showed 30–50% incidence, even with modern pest control measures. The traditional materials and methods created inherent resistance modern treatments struggle to replicate. Chapter 12. The regulation that prohibits excellence. Modern textile regulations, flammability standards, chemical content limits, labeling requirements serve legitimate safety and consumer protection purposes. But they also create barriers to traditional textile production. Flammability regulations, implemented after numerous fire tragedies, require textiles to pass standardized burn tests. Natural wool and linen are inherently flame-resistant. They're difficult to ignite and self-extinguish when flame source is removed. Synthetics burn readily and produce toxic fumes. Yet regulations are written for synthetic fabrics, requiring chemical flame-retardant treatments even for naturally flame-resistant materials. These treatments are toxic brominated compounds or phosphates that raise environmental and health concerns. They're also temporary. Washing gradually removes them, requiring retreatment or replacement. Traditional wool and linen without treatment meet performance requirements but not regulatory specifications, creating compliance issues. Chemical content regulations restrict certain dyes and mordants. Lead-based pigments are prohibited appropriately, as lead is toxic. But the regulations sometimes restrict traditional mordants like copper sulfate or iron mordants that have been used safely for millennia, requiring modern substitutes that don't perform as well. Labeling requirements mandate fiber content percentages, care instructions, and country of origin. These seem reasonable, but create complications for hand-produced textiles where fiber content varies. Care requirements depend on specific processing, and country of origin is ambiguous for materials sourced internationally but processed locally. The regulations weren't written to prohibit traditional textiles, they were written for industrial manufacturing and applied universally. But universal application creates friction for small-scale traditional production, requiring expensive testing, complicated compliance procedures, and legal consultation that artisan producers struggle to afford. Some traditional textile producers operate in regulatory gray zones, selling art pieces rather than functional textiles to avoid flammability standards, or limiting production to personal use and gifts to avoid commercial regulations. This allows craft to continue, but prevents traditional methods from competing commercially with industrial textiles. Reform would require performance-based regulations acknowledging that traditional materials and methods can meet safety and quality goals through different means than industrial manufacturing. Some jurisdictions, particularly in Europe, have moved toward this approach, creating specialty categories for traditional crafts. But most regions apply one-size-fits-all regulations that disadvantage traditional production. Chapter 13. The Museum that becomes tomb. Museums worldwide hold hundreds of thousands of textile artifacts, clothing, tapestries, carpets, flags, religious vestments. These collections face existential crisis. The medieval pieces are stable and will survive indefinitely with basic care, while modern pieces are rapidly degrading despite expensive conservation efforts. The asymmetry creates difficult allocation decisions. Conservation budgets are finite. Should resources go toward preserving medieval tapestries that will survive anyway, or toward stabilizing 20th century textiles that are actively degrading? The logical answer is prioritizing urgent needs, the degrading modern materials. But this means accepting that historically priceless objects are less stable than the ancient artifacts they were supposed to improve upon. Some museums are making hard choices, acknowledging that certain modern textile collections can't be saved. The materials acetate, early polyesters, poorly dyed cottons are inherently unstable. Conservation can slow degradation but not prevent it. These collections are being documented extensively, photographed in detail, fibers sampled for analysis, construction techniques recorded before inevitable deterioration makes them unusable. The documentation preserves knowledge, but the physical objects are lost. Medieval textiles face different problems. The materials are stable, but the knowledge of how they were made is disappearing. Museums hold thousands of medieval textile artifacts, but employ perhaps 50 to 100 conservators worldwide with expertise in traditional textile techniques. When complex restoration is needed, replacing damaged sections, recreating missing elements, finding practitioners capable of working at medieval quality levels is increasingly difficult. Some institutions are training conservators in traditional techniques, creating specialized programs in natural dyeing, hand spinning, and historical weaving. But the scale is tiny, perhaps 20 to 30 students annually worldwide entering this field. The skills shortage will worsen as elderly practitioners retire faster than new ones are trained. The irony is stark. The oldest textiles are the most stable and require the least intervention, while the newest textiles are the most fragile and require the most conservation effort. We're preserving the past while losing the present, and the museum's storage vaults are filling with materials that won't survive for future generations to study. Chapter 14. The fiber that refuses to die. Medieval textiles survived through engineering superior materials, careful processing, optimized construction. But they also survived because they were made to be kept, repaired, and maintained across generations. The concept was life cycle design before the term existed. Tapestries were made with extra material at edges, allowances for rehemming if edges frayed. Clothing was constructed with large seam allowances, enabling alterations and repairs. Vestments were designed to be disassembled and reconstructed as styles changed or as fabric wore. Nothing was disposable. Everything was maintainable. This extended lifespan exponentially. A tapestry developing damaged area could be reweaved, the damaged section cut out, new threads woven in, the repair nearly invisible. Medieval tapestries show evidence of multiple repair campaigns across centuries, each adding decades of additional service life. Modern textiles are designed for disposal, not repair. Machine sewing uses narrow seam allowances, no material for alterations. Constructions often involve adhesives or ultrasonic welding that can't be disassembled. When damage occurs, repair is often more expensive than replacement. The result is textiles treated as consumables rather than assets. Medieval repair culture created social infrastructure around textile maintenance. Every household had spinning and mending tools. Women primarily spent substantial time maintaining household textiles, extending their service lives through continuous care. This labor was considerable but distributed a few hours weekly rather than large occasional expenses. Modern culture outsources textile maintenance to industrial laundries and disposal to landfills. We've eliminated the maintenance labor but replaced it with continuous purchasing. Whether this represents progress depends on how you value time versus money versus material durability. The textile itself, in medieval context, was never finished. It was always being maintained, always being adjusted to current needs, always being prepared for next generation's use. This created psychological relationship where textiles were partners in life rather than products consumed. The shift from maintenance culture to disposal culture represents profound change in how we relate to material objects, with implications extending far beyond textiles. Chapter 15. The thread that holds memory. You cannot buy medieval quality textiles commercially. The materials don't exist in mainstream supply chains. The craftspeople are rare and expensive. The market is minuscule, measured in dozens of practitioners serving hundreds of clients globally. For practical purposes, the technology exists only in museums and craft preservation programs. But the lesson transcends the specific techniques. Medieval textiles teach that durability requires accepting slower production, higher initial costs, and different aesthetic priorities. The fabric must be dense, which requires more material and time. The colors must be naturally dyed, which limits palette and increases process complexity. The construction must be robust, which means visible structure rather than hidden seams. These requirements conflict with modern consumer expectations: fast fashion, unlimited color options, invisible construction, cheap prices. Reconciling medieval durability with modern desires is difficult, perhaps impossible. We can make textiles that last 500 years, but not textiles that also meet modern commercial requirements. The medieval textile is waiting in museum collections, in craft workshops, in the hands of elderly practitioners passing knowledge to rare apprentices. It's showing us what's possible when craftspeople prioritize longevity over efficiency, when materials are selected for strength rather than softness, when construction optimizes for centuries rather than seasons. The fabric itself is patient. The tapestries will hang for another 500 years, outlasting the synthetic textiles created to improve upon them, demonstrating that the slowest, most labor-intensive, most expensive methods produced results the fastest, cheapest, most efficient methods cannot match. The thread that holds memory is still being spun, barely in scattered workshops by aging hands. It's still being woven into cloth that will outlast nations. It's still being dyed with colors that won't fade, while civilizations rise and fall. The question is whether we remember why permanence matters before the last practitioners die, and the knowledge becomes purely historical, studied but not practiced, understood but not embodied. The textile doesn't need us. It's already woven, already dyed, already surviving. We need it to remember that not everything must be replaced, that some things are worth the time they take, that the most valuable materials are those that refuse to die even when everything around them has turned to dust.